Okay, so let's continue talking about free groups today. So recall we have already defined the free group on two generators which we called A and B, but there's nothing really special about a group with just those two generators. More generally, we can talk about the free group F generated by any set S. So here S can in fact be any set, finite or infinite. It doesn't really matter. And we can talk about the free group generated by that set as follows. So of course it really only makes sense to talk about non-empty sets for the free group. So how does one define it? Well, we just follow the same steps that we followed when we defined the free group on two generators, which are the following. So recall, what did we do first? We looked at the augmented set S hat. So I'll do the same thing here. The augmented set S hat is defined to be S union another set S prime. And what is S prime? S prime is a set which has the same number of elements as S, but we'll call the elements as, so let's say it's a set whose elements look like X prime, where X is any element of the alphabet S. So recall S was the alphabet and S prime is just sort of the primed alphabet, just got primes on top of the alphabets. Okay, that's the augmented set S hat. Then our starting point was the monoid, which is the set of all words using the alphabet S hat, both letters and their primes. So we considered this, and we know that this is not quite a group, but it's got a very useful operation, that of concatenation. The same definition applies as before, and the concatenation has the following properties: that it is an associative operation and it's got an identity element, which in this case as before is just the empty word. Okay, so well, what do we need to do next? We need to define an equivalence relation like we did in the case of the free group on two generators. So this is what we achieved by means of what we call the basic rewriting rules. So what were these? These rules are the following. If you recall what it was before, it said, you know, A prime can be replaced with the empty word, A prime A, similarly B prime, B prime B. Each of these can be replaced with the empty word. Okay. So here it's the same thing. Instead of A, B, you have many more alphabets. So let me write this out in general as follows. Whenever I see an alphabet X next to the alphabet X prime, I can replace this word of length 2 by the empty word. Similarly, if I see X prime followed by an X, I am allowed to replace it with the empty word. Okay. And in fact, the way we wrote the basic rewriting rules, there are also the rules in reverse. So X prime is replaceable by the empty word, X prime X, I can replace it. These are two rules, and the opposite rules also are available. I can replace the empty word with X prime, or I can replace the empty word with X prime X. So there are, in this case, 4 basic rewriting rules for each alphabet in S. Okay, and we define the following thing. So this is for every X in S, and we defined an equivalence relation on words as follows. So we have an equivalence relation which is the following, that two words W1 and W2 are said to be equivalent or related to each other if I can go from W1 to W2. So if there exists words Z1, Z2, Zk between W1 and W2 in this way. So let me write this as, if there exists a chain of words such that each arrow is a basic rewriting rule, is obtained. So each of these arrows which connects these successive words is obtained via some basic rewriting rule. Okay, in other words, by successively replacing X primes by empty or X prime X by empty or the reverses of those rules, you can go from the word W1 to the word W2. Okay, just like what we saw in our earlier example. And as before, the definition of the free group is G is defined to be the set of equivalence classes of the set of all words under the equivalence relation tilde. Okay, so this, as before, is going to be our set G, and the operation is the same thing. So if I take two words W1 and W2 and I look at their equivalence classes in G, so I look at W1 in G, well, I look at the equivalence class of W1, that's an element of this set G, this is an element of G. The product is defined as before to be, you take the concatenation of the two words and then you look at the equivalence class of the concatenation. Okay. Now, since it's the verification of the properties is very closely analogous to what we have seen already for the case of two alphabets. So, I am just going to leave this as an exercise for you to try your hand at how these arguments work in general. So, here are the various exercises. I suppose one is show that this is really an equivalence relation, is an equivalence relation. So, that is one, and two, that under this product that I just defined, so G with this product dot is a group. Okay, in other words, the product is associative, it has an identity, and most importantly it has inverses. Okay, and you will observe that, like before, if I take the word, just a single alphabet X coming from the set S, and it's a word of length 1, I look at its equivalence class, and somehow this is how we motivated the entire definition. So, we needed to find an inverse for this word X, and like in the earlier case, this inverse is just the word X prime. So, this is for all X in S. So, maybe that's part 3 of the exercise. Show that in this group G, the inverse of the singleton word, the word of length 1 X, is in fact the word X prime, okay, also a word of length 1. Okay, in fact, that will be one of the things you will show when you show that it's a group. Okay, so this is sort of how you define free groups in general. So, G is what's called the free group on the set S, and the notation we introduced was this sort of curly F of S. Okay, so let's get our hands on an example. So, here's sort of something even simpler than the free group on two alphabets. We could look for the free group on a single alphabet or a single generator. So, suppose my set S has just a single element A, okay, and so now I try to understand what the free group on this single alphabet A looks like, and here's my claim. This free group on a single alphabet is actually isomorphic to the group of integers under addition. In other words, it's an infinite cyclic group. Okay, so let's prove this. So I'm going to prove my claim. So observe, what is it that the free group, I mean, how did we construct it? We'll first have to look at words in the alphabet A and A prime. So the typical word here will look like some A's and then some A primes and some A's again and some number of A primes and so on and so forth, right? So this is all the word can have A's and A primes which occur in some order, some number of times and so on. Of course, all words are finite, so it ends somewhere. So this is a typical word in S hat. And then the free group itself is obtained by looking at the equivalence relation on the set of words in which you are allowed to sort of collapse an AA prime and make it empty, or expand an empty word and make it AA prime or A prime A, and so on. So we however need to show that the free group is actually isomorphic, I claim, to just the ordinary group of integers. Okay, and intuitively it's sort of clear why, because whenever you see a string like this of A's and A primes, what's of course going to happen is that every time you see an A and an A prime together, so for example this A and A prime, the basic rewriting rule will say you can actually erase it, right? So this sort of goes away. Now again another A and an A prime end up being together, so you can get rid of them using the basic rewriting rule. So every time you see an A and an A prime, off they go, A prime, A prime. Okay, so let me just complete this word to something. So let's suppose these last few letters were A prime, A prime, A prime, A. Okay, so again I scan this and I notice that here's an A prime A, which again can be made into an empty word. So I get rid of all these. So observe that every time an A and an A prime occur together, you can get rid of them. And finally, after you have done this process sufficiently many times, I mean as many times as you can, you will find that the word that you finally get has only A's or has only A primes. Okay, it has some number of A's or it has some number of A primes. And so that number of A's that you are left with, that's really the integer that we are going to map that word to. Okay, so observe, to construct an isomorphism, what we need to do is to construct a map from the free group to the integers, or from the integers to the free group. Okay, so let's do it in this order. So we'll try and construct a map from the free group to the integers. Okay, now of course a free group is, so this is what I want to construct a isomorphism of groups. Okay, so I want to construct a group isomorphism. But as an intermediate step, let me try doing this at the level of words. So let me look at all words in A and A prime and define a map from that to the integers. Okay, so I'll call that map phi, and here's my map. So I write my word W. It's some A's and A primes, as I said, some bunch of A's and some bunch of A primes. Now my map does the following. It maps W to the number of A's in W. So it's the number of A in the word W minus the number of A primes in W. Okay, number of A prime in W. Okay, so I don't want to put that also in quotes, so probably confused. So let me get rid of this as well. So let's do one thing. Let me just put this in a different color. So I'll say it's a number of the alphabet A, number of occurrences of the alphabet A minus the number of occurrences of the alphabet A prime. Okay, so this is of course an integer, could be a positive or a negative integer. And let's see what properties this map has. So observe, if I have a word W, so here's the first key observation, that suppose I have a word W and suppose I perform a basic rewriting rule on W. Okay, so I transform W to some other word. So maybe let's say if I have a word W1 and I perform a basic rewriting rule. So let's say basic rewriting, which means what have I done? I've either collapsed an AA prime and made it empty, or A prime A empty, or expanded an empty into an AA prime. Observe, the basic rewriting rule always has the same number of A's. It either collapses, it either removes the 1A and 1A prime, or it increases the number of A's by 1 and number of A primes by 1. Okay, in other words, the basic rewriting rule does not change this difference that we are talking about. The number of A's minus A primes remains constant. Okay, so if W1 and W2 are related like this, then certainly this number phi of W1 and the number phi of W2 are necessarily the same. Okay, now as a corollary to this observation, if I have two words which are equivalent under the equivalence relation, which means I can go from W1 to W2 by means of a sequence of basic rewriting rules. I may not be able to go in one step. Still, the same property holds because it holds at every step. Okay. So, what does this mean? Two equivalent words necessarily have the same value of W. So, I can in fact define a map. So, what this means is that I can think of phi as actually giving me a map from the set of equivalence classes, okay, which is what we call the free group. In other words, given a word W, look at its equivalence class, I can associate to this equivalence class the number phi of W. Okay, and this new map I will call as phi bar. Okay, it's a map from f of s to z. Okay, so observe, this is well defined. In other words, it doesn't depend on the representative W that I picked for the equivalence class. Okay, why? Because of what we just said. What we just said above, if instead of W1 I had picked W2 as my representative, or maybe here if I had instead of W1 I picked something equivalent to W1, then the value of phi would have remained the same. Okay, so I can just go ahead and pick any representative of my class and define my map to just be phi of that. Okay, so this is the number of a's minus number of a primes. This defines gives me a well defined map from the free group on S to Z. S, remember, is just a singleton here. So firstly, it's well defined, and now I claim that this is actually the isomorphism that we want. Okay, so first let's show that it's a group homomorphism. So recall, what does homomorphism mean? I must take two elements W1 and W2 in my group f of s. I should multiply them out in the group, and then my answer should equal phi bar of W1 times phi bar of W2, but times is the product on the right hand side is computed in the group Z. It's computed in the range of this map. In other words, that operation here is just a plus, the usual addition in the integers. So this is phi of W1, phi bar of W1 plus phi bar of W2. This is what I need to prove. So this is what it means to say that phi bar is a homomorphism. Okay. So let's compute each side and see whether this equality holds. So let's check what the left hand side is. By definition, this is phi bar evaluated on the product is the concatenation of these words. Now look at this concatenated word W1 star W2. Phi bar of this equivalence class is just going to be the number of a's in the concatenation minus the number of a primes in the concatenation. Okay, but observe, the concatenation of two words is just put W1 first and then write W2 next to it, right? So if I am trying to count how many a's occur in the concatenation, well, I just have to see how many a's occur in W1. I may see how many a's occur in W2, and it's just the sum of those two numbers. Okay. Similarly, the number of a primes in the concatenation is just the sum of the number of a primes in W1 and W2. Okay. Okay. So what this means is that this answer is nothing but phi bar of W1, which means the number of a's minus a primes in W1, plus phi bar of W2, the number of a's minus a primes in W2. Okay, so that's the proof of the homomorphism property. Okay, now let's look at property B, which is one-to-oneness. So let's prove one-to-one now, and then we'll prove onto. So why is this map one-to-one? Since it's a homomorphism, we just need to check the following property, that if a word maps, if the equivalence class of a word maps to the identity element of Z. So, the identity under the addition, remember, is 0. So, suppose some equivalence class maps to 0, then we need to prove, that this equivalence class must be the identity element of the free group. And remember, so this should be the identity element of f of s, which, if you remember, and which you probably checked, is nothing but the equivalence class of the empty word. Okay. So, let us prove this. So, let us analyze what this means for a second. So, we are trying to understand what it means for phi bar of a word to be 0. Okay. By definition, phi bar is the number of a's minus a primes. So, the fact that phi bar of a word is 0 just means that the word has an equal number of a's and a primes. Okay. So, let us go here. The word w has as many a's as a primes, has an equal number of a, the alphabet a and the alphabet a prime. Okay. So, what does that mean? It means that if you scan this word from left to right, just like we were doing before. So, let me write a word like this, a prime, a, something like this maybe. So, this is what the word looks like. It has an equal number of a's and a primes. So, it has at least one a and a prime. Okay. Let us assume that the word is not empty. Okay. If the word is already empty, then you are done, because you have to prove that finally this word, the equivalence class of w, is just the equivalence class of the empty word. Okay. So, if w is not the empty word, then w looks like this, in which there are at least with, let us say, k occurrences of a's and k occurrences of a primes. Okay. Now, where k is at least 1. Now, you scan the word from left to right. Okay. There has got to be at least one place where an a and an a prime occur next to each other. They occur consecutively, right? That's you really can't avoid that if you have got k a's and k a primes, and where, I mean, any word which has both a's and a primes already must have at least one position where an a and an a prime come next to each other. Okay. One way of saying it is, you scan the word from left to right, you look at the first letter. If it's an a, then at some point you must get to an a prime, right? So, the place where it transitions from a to a prime, that place will have a subword of the form a prime. Okay. So, you pick the a and a prime coming next to each other. It could be a prime or a prime a. So, let us do this for example. So, find a place where I have a prime a, and using the basic rewriting rule, I get rid of that entirely. Okay. So, from this I can form another word in which, so using a single basic rewriting rule, what I have been able to do is to find another word in which still it has an equal number of a's and a primes, but that number has come down by 1. It is k minus 1 a's and k minus 1 a primes. Okay, now repeat the argument. Again, if k minus 1 is at least 1, then it means this word is not the empty word. That means surely it has both a's and a primes. And again, find any one location where an a and an a prime come next to each other, and you get rid of them using the basic rewriting rule. So, again I can do this. Okay, so what have I generated? Another word, but now it's got k minus 2 occurrences of a's and k minus 2 occurrences of a primes. Okay, and so on. So, you can see that as long as this number k minus 1, k minus 2, etc., as long as these numbers are at least 1, you can keep doing this. So, what it means is, at some point you will be left with the case when this number becomes 0. This number keeps decreasing by 1 each time, and at some point it's got to reach 0. Okay, so what does that mean? When it reaches 0, it just means that the resulting word at the last step that you have has 0 A's and 0 A primes. In other words, this is just the empty word. Okay. In fact, in the one preceding step, the word must have had a single A and a single A prime. So that word must have looked like either A prime or A prime A. Okay, that was the one preceding step. And of course, the possibilities for each step prior to that are many more. Okay, but at the very end, you are going to necessarily reach the empty word. Okay, so what does that mean? You can reach the empty word from the original word W. Right, I have gone through a sequence of basic rewriting rules and I have gotten to the empty word, which means that W is in fact equivalent to the empty word. In other words, the equivalence class of W is the same as the equivalence class of the empty word. Okay, which is what I wanted to prove. So this proves one-to-oneness, and let's finally prove the ontoness. So part 3 of the proof of isomorphism, I need to show that this map phi bar is onto. Okay, what does that mean? I need to show that, so recall phi bar as a map from f of s to z. Given any integer n, I must show that there is some word, some preimage, right? I must show that there is some word W whose equivalence class maps to n. Okay, so this is very easy to manufacture. So observe, if n is at least 1, then what is this word which maps to the number n? I can take W to be, so let's write this out here. If n is at least 1, I can take W to be the word which has A occurring n times. Okay, if n is negative, if n is minus 1 or lower, I can take the word which looks like A prime, A prime, A prime. So now I should take minus n times or modulus of n times. Okay, so observe, this is the first word has if I look at phi bar, which is number of A's minus A primes, it's n for the first word, and because it's n minus 0, there are no A primes. For the second word, it's 0 minus n, because there are no, it's 0 minus, not 0 minus n, but rather 0 minus modulus of n. Okay, so in this case, mod n is the same as minus n, so maybe I should write as it occurs minus n times. So if you compute phi bar, you will again see it is n. And then finally, if n is 0, of course, that's the easiest case. I can just take W to be the empty word, and phi bar, the empty word, is of course just 0. Okay, so we have managed to show that this is an isomorphism, and so that's sort of a nice tractable example. But sort of a thing to keep in mind is that as soon as your, so this is done, that proves our claim that f of a singleton, the free group, is just isomorphic to the group of integers. But as soon as the set S has 2 or more generators, this becomes a vastly more complicated group. Okay, if I take the free group on 2 generators A and B, then this is a much more complicated group than the group of integers, for example. Okay, in particular, this is not going to be the group of it's not the group Z2, for example. So observe, while this is isomorphic to Z, f of this is very far from being true. Okay, so this is not at all the case. Okay, so these groups are, Z2 is in fact an abelian group. It's got 2 generators, but it's an abelian group. F of AB, the free group on 2 generators, is of course non-abelian. The word AB and the word BA in this free group will turn out not to be in the same equivalence class. Okay, so in order to sort of better understand some properties like this of the free group, so for example, I just mentioned this is a non-abelian group. In other words, if I take the word AB in this group and I look at the word BA in this group, then the equivalence class of AB is not the same as the equivalence class of BA. So I am talking about the free group here on 2 generators. Okay, So to prove things like this, even basic facts about free groups, I mean, you could prove it just from the definition, for example, that there are no basic rewriting rules which will help you go from here to there, but there is sort of a nice conceptual way of understanding these free groups, and that's the notion of its universal property, and that's something that we'll take up in the next lecture.